start, I guess. Okay, so welcome to week 4. Today, like I was mentioning earlier, we're going to mainly be talking about designing for manufacturing and stuff like that. We're going to be talking about 3D printing today. So it's a topic that I personally have a lot of interest in, and it's something that I think is becoming more and more mainstream for most of us students. To start, I'm just going to introduce the final. I have talked about it in previous classes, but I guess this is technically the formal introduction of this project. You've definitely seen this slide before. But now that you've kind of been through a good amount of this class, this slide might make a little bit more sense to you. Basically, you're going to create a model, using your brain. I'm not going to tell you what to do. You have free reign to do whatever you like. It obviously can't be something we already did in class because, plagiarism or something. You need at least 5 design features, which if you've kind of been paying attention in class, that's not a very high bar to meet, like especially with the, like the hair dryer assignment. I'm pretty sure you meet 5 already. So in terms of complexity, we're not asking for all that much, but it is just kind of that way to give you a lot of freedom to make something that you really want, right? So you can make something that is practical for yourself or just something that's really cool. We just kind of want to give you, free range to do something awesome. I would say a vast majority of people use a lot more than 5 design features, but I get it. We're all students. We're all really busy. And if you really just need to kind of throw something at me and turn something in, that's totally understandable. But yeah, the last thing is that it must be designed with manufacturability in mind. So that's a big majority of what I'm going to be talking about today, because, we want to set you up for success for your finals so you don't get like a pile of filament that's all like sad and just like a blob. So we're going to talk about that. Hopefully you're going to make something cool. There might be some people picking up their finals from the previous session today, so there's a box of them here. If you're curious and you want to check them out, feel free to do so. But yeah, I think you've also seen this slide before. Again, these are some previous finals from I think a couple of years ago. They all definitely have more than 5 design features. So, a lot of people spend a good amount of time on this. This isn't like the bare minimum though. This is like, these are very exceptional final projects that we like to display. So if you're shooting for something more simple, that's totally fine too. But yeah, designing with manufacturability in mind. Okay, so if you didn't know, there's kind of 2 main categories when it comes to manufacturing. Obviously, your part needs to be made in some way. And they usually break it down into these 2 segments. The first one is what we call subtractive manufacturing. A lot of engineering terms just kind of have the description of what it is in the name. It's subtracting stuff, right? So you start with, some material, and then you cut away at it, or you grind away or sand away. You remove it in some manner, right? To the point where you have your final product, right? So in this case, there's some tool that cuts away at this block looking thing, and now you have that nice curved piece. So this is pretty common manufacturing, or there are many common manufacturing processes that, utilize subtractive manufacturing. You might have seen a lot of it if you're, ever been in some kind of shop where people make stuff. A lot of these machines can end up being kind of expensive, especially when you're getting into like high precision milling machines and grinders and stuff like that. Some of these machines can cost north of like hundreds of thousands to maybe even millions of dollars if they're super, super fancy. So, they're pretty awesome. You can get some insane precision out of them, but for, most students like us, we don't really have like a garage and like, $20,000 burning a hole in our pocket to buy a milling machine. So a lot of these processes, typically aren't available to us unless we know someone or have access to it. You can do some of them with, drilling with like a hand drill or a drill press. So there is like a range of prices. But for the most part, we're going to be talking about additive manufacturing for this class. But this is, an option. And every time you design a part to be made, you have to think about what machine it's going to be made from, because every machine has its own limitations. We're not going to really be talking about these limitations today, but yeah, if you ever want to do research or ask me, I'm happy to talk about it. The other manufacturing process, or at least the type, is what we call additive manufacturing. A lot of people think about 3D printing because it's pretty popular now. That's mainly what we're going to talk about today. But the concept is you kind of start from nothing. You have some kind of tool that, deposits a material in some manner and builds it in a way where you have your product, right? So this is kind of a really basic example of how a 3D printer works. We're going to talk about it more later. But if you didn't know, this isn't the only additive process that exists out there. So the other big one in the scene is injection molding. It's typically a lot more expensive and, out of scope for, most consumers, because you need to spend, thousands, maybe tens of thousands to create a nice mold for your injection molding machine. That's super expensive as well. So we're going to be talking about 3D printing. But one of the things to note is that the 3D printing industry does kind of benefit from like all the advancements we've made in injection molding, because they can utilize similar materials. So when you think about Lego and stuff like that, it's made of something called ABS. I'll talk more about materials next week, but like ABS is a pretty common 3D printing material. And if you can 3D print it, you can probably injection mold it too, or the other way around. There's definitely a wide range of applications for 3D printing. It's growing every day. Someone will find some application to apply it to. It's pretty awesome. In the past, it's mainly been reserved for rapid prototyping, but a lot of people are using 3D printers, in their homes, or they have big print farms to create full-on products that people just buy. So it's definitely becoming a lot more common. It's pretty cool to see, but here's some applications. I'm sure there's more out there that I haven't listed here, but yeah, it's pretty cool. In terms of the types of 3D printing, there's kind of 3 categories that I usually think about. There's definitely more out there, but these are kind of the 3 main ones. The first one that I'm talking about is SLS, which is selective laser sintering. You basically take a very fine powder of some kind, usually like a nylon or something kind of similar to that. You lay a very thin layer of it, and then you use a laser to sinter it. You basically, have one layer, you cover it with more powder, shoot more lasers at it, and you do it over and over again until you have your part. So SLS is pretty cool, but typically it's not something that someone's going to have in their bedroom or their garage. So I'm not going to talk about it too much, but it's pretty awesome. There's a different or a similar kind of printing to SLS called SLM, which is just the same thing, selective lasers, but they utilize metal. So you can get stuff like metal 3D printed. And if you're in kind of the like high-end performance like 3D printing scene, people will like get their tool heads and stuff for their printers like metal 3D printed and stuff like that. It's pretty cool. But typically you're going to have to pay some kind of service to get that done, because SLS or SLM machines are pretty expensive. In terms of desktop manufacturing, SLA is a lot more manageable. You usually use some kind of resin. So if you've ever used epoxy before, it's kind of similar to that, where you have some kind of liquid. In this case, it's typically something that is UV, or it cures with UV light. So you basically have a TV on the bottom of your machine. It shines a light in a specific area that's UV, and then it'll build up layers and layers until you have your part. So SLA is pretty cool. You can get really nice details out of it compared to some other processes. But yeah, personally, I don't know a ton about SLA, but it is pretty popular for people who like to do like Dungeons and Dragons and stuff, like to print miniatures, stuff that really needs a lot of high resolution. They also use it in other fields like dental practices, I believe, where they make like night guards and stuff with resin machines. So it's kind of one of the benefits of 3D printing. You can get really high detail and like high customizability without a very high cost. So that's one of the reasons why 3D printing has become so popular. But the one thing that I haven't talked about yet, which you're probably thinking about, is FDM 3D printing. So that's kind of the main topic for today. We're going to talk about, what it is and how you might design your parts to cater towards an FDM design. So there's technically two terms for FDM because FDM is technically like a trademarked like name or something. I think Stratasys like has a trademark on FDM. So if you ever look it up, most companies will use FFF instead, but they basically mean the same thing. So I might use those terms interchangeably today, but they're just the same thing. Basically, how it works is, my analogy is it's a very fancy hot glue gun connected to a robot, but instead of hot glue, it's some kind of filament, which is usually some kind of plastic. Basically, you have some kind of extruder motor that will push that material through a very hot nozzle, and then with that fine control of the motor and the motion system of the 3D printer, you can precisely place the material where it needs to be. It'll usually print in layers, so it'll print a 2D profile, it'll go up a little bit, and it'll do that over and over again until you have your part. So a lot of people say it's 3D printing. Some people call it 2.5D 3D printing because you're basically stacking a bunch of 2D profiles on top of each other to get a 3D part. But that is changing. Some people are doing like non-planar printing and stuff, which is pretty cool. But yeah, I'm guessing a good majority of you have already kind of seen a 3D printer in your life now. They're pretty popular. They've gotten pretty accessible, so it's pretty awesome. But yeah, now is the time where I'm going to just start yapping about different parameters. So, again, some of these are important. Some of these, might be, it might be a little bit complicated, or, there's just a lot of information. But anyways, there's basically like a bajillion parameters that you can change when it comes to 3D printing. If you think of like a 2D printer, you're a lot more limited in how the printer will do stuff. You can like change some things like the DPI, which is like kind of like the dots per inch per square inch, to see if you like increase the resolution and stuff. But when you're working in 3 dimensions, there's a lot more stuff to take into account. So the layer height is definitely one of the first things that you might change. Though typically it's something you kind of set when you first start printing, and then you typically just kind of leave it there unless there's some special reason for changing it. But basically it just controls how fine each layer is. Again, like I was saying, it's kind of like 2.5D, so it'll stack profiles on top of each other, and you can change the thickness by changing the layer height. So increasing that layer height or increasing that thickness there will, be a lot faster just because there's less layers to produce. But that might reduce the resolution, especially in the vertical direction. So you can see on the left side of the slide, there's like a 0.8 millimeter layer height, and you can see the lines pretty clearly. But as you go farther and farther to the right, when they get more fine, it's a lot harder to see. So depending on your application, you might want to consider that. I'd say the standard layer height is usually in the range of 0.2 to 0.1. People find that as like a very nice balance between quality and speed. One thing to note is, technically speaking, each layer is a failure point when it comes to your 3D printed designs. So in some cases, it might be a good idea to increase your layer height because that reduces the number of places parts will fail. 3D printed parts, at least in FDM cases, are the weakest on the layer lines. So they typically like to shear on the layers because they don't always bond perfectly. So having less layers, reduces the chances of failure. So if you're looking to make really strong mechanical parts, sometimes upping that layer height can give you some benefits. But obviously, if you're printing, things that you want to look really nice, decreasing that layer height will help you with that resolution. Okay. Perimeters is one that I typically see myself changing very often. It's basically how thick the 3D printed walls are. If you didn't know, most 3D printed parts are actually hollow. So I guess, but I guess I can pass this around. Someone made a rocket, but you can see if this looks solid, all of them are wrong here. And okay, well, the next slide's about infill, but most 3D printed parts are hollow. So controlling the outside thickness is a very important parameter to keep in mind when you're making parts. Because, if you have a very thin outer section and you want it to be strong, it'll probably break. So typically I change the number of perimeters if I want more strength before I change infill. I'll talk about infill in a second. But typically it's measured, in either, the dimension or the number of perimeters. I would say the standard perimeter count is usually like around 3 or 4. But if you want something stronger, you can increase that pretty easily. Obviously, when you increase the perimeters, you're adding more material. It's going to get a little bit heavier, but it'll be stronger. It'll take a little bit more time to print, but depending on what your needs are, that's just kind of how it is. If you reduce it, the opposite happens. It's faster, but it's weaker. So again, these are all parameters that are really based on your application. If you're printing like desk toys and stuff, 2-3 perimeters probably more than enough. But if you are printing stuff that subject to high loads, you want to increase that. So yeah. Infill is what I was talking about earlier. Again, 3D printed parts are usually hollow on the inside because most of the strength comes on the outside. Hence why I typically increase perimeters before infill. But if you want, you can kind of balance the two. Usually 3D printed parts range from about like 10 to maybe 30% infill. I'd say most people stick to maybe 10 to 15. But if they're making more, parts that are subject to more stress, I typically do like 25% with 4 perimeters. But depending on the application, you can go a lot higher. Like there's stuff that I 3D printed for my car, and I just do like 100% infill because I just want it to be solid. But for most applications, you don't need it to be 100. It just wastes time and material. But yeah. Okay, supports. Okay, I have some good examples. So there will come times where your design may have some limitations, where you might need a certain geometry, but that geometry would technically be impossible to reproduce on, a printer without some kind of help. And that's where supports come in, right? So I guess I'll pass this around. This is the other half of the rocket from the final. It's typically when something overhangs outwards. In this case, you can see on the slide, this kind of cylindrical feature is sticking out. Again, 3D printers, they're not like magical tools, and they're subject to, gravity and stuff. So if you tried to 3D print this without supports, this area would just droop, right? Because the nozzle's hot, the plastic is molten when it comes out, so it's just going to droop. So you need something underneath to support it. That's why it's called supports. So it's kind of a sacrificial material that people use to make their parts work in the way that they need to. Obviously, if you're printing with supports, it's going to take more time because you're, using more material. And, it's going to cost more because you're using more material. The other thing is you need to remove the supports when you're finished. So that can get kind of tedious depending on your design. So as the designer, you have the ability to try to minimize the amount of supports that you need. So when I talk about designing for manufacturability, this is one of the things I'm going to be looking at when I'm grading for the finals. You know, obviously, if you have a geometry that just needs it, then just use it. But in many cases, if you change the design slightly and, you know, made things in certain ways, you can eliminate the need for the supports. So minimizing it would be nice. You know, it's less work for me, a little bit less print time. And, you know, sometimes if your parts are super, super small and they have supports around them and you break the supports off, you're going to break your part too. So that's something to keep in mind as well. So minimizing supports is ideal, especially because you're designing the part. But if it's not avoidable, then sometimes you got to use them. Okay, so this is an example of supports. I guess I'm passing it around, so it's probably a little bit easier. But you can see here, you know, the H and the T were printed vertically, and because of that, you know, the H may not have needed it, but the T definitely did because it would have drooped. But I guess this is an interactive part of this lecture. But is there anything that you think this person could have done to eliminate the need for supports while retaining this geometry? Yeah, you could print it upside down. You could also just print it flat too, right? So print orientation is something that you might want to think about when you're designing stuff, because sometimes people print things in really strange ways to minimize the amount of supports. The other reason why people might do that is to help with surface finish. But last class, someone sent me a B-2 bomber for their final project, and it was really cool, right? It was an awesome model, but, you know, especially, or a lot of things like planes and stuff with really organic features don't have a nice surface to kind of sit on. And if I tried to print the B-2 bomber flat, the surface finish on the bottom would have been really, really bad. So what I ended up doing is I printed it like nose down, and I just used supports to support the wings all the way up. So they had a good surface finish. This is definitely like kind of wasteful because, you know, this is a lot of support, but, you know, print orientation can definitely impact how your print comes out. But yeah, definitely keep print orientation in mind. Orientation also affects how strong your part is going to be. So, you know, when it comes to cylindrical shafts, the, you know, logical idea to print it for the best quality is printing it straight up and down like this, right? But, you know, there's layer lines going all the way up. And then if you have something, you know, bending it, I don't want to break this final, but you can easily split the layer lines, right? So when you're 3D printing shafts and stuff, and they're all on the layer lines, there's, you know, potential for failure. So some people will print like cylinders sideways to make it stronger, but then it's kind of a trade-off because it's not as round, right? So those are just kind of some of the limitations that people typically run into when making 3D printed parts. But yeah, enough yapping for now. We're gonna actually do the assignment now. I think it's a little bit easier to visualize some of the parameters I'm talking about when you actually do it. So we're gonna just slice apart real quick using a slicer. So we're gonna download Prusa Slicer. Should be pretty quick because it's not a big file like Fusion. So yeah. Out of curiosity, who's like used a 3D printer or like has a 3D printer? Okay, so some of you have. Okay, cool. All right, so under the resources tab, there's this link here. And then you can just download it. I'm pretty sure I already have it installed. Okay. So while this is launching, I'm going to talk a little bit more. Hopefully save some time here. Um, but yeah, we're basically downloading a slicer right now, or at least I hope you are. There's definitely other slicers out there that you can use. Not for this assignment, but just like a lot of people use different slicers, including myself. Um, and at the end of the day, they all kind of do the same thing. They convert your 3D model into a bunch of commands for the 3D printer to follow. Again, it would be a little bit easier to see and visualize once we use it. But it basically creates a toolpath for your 3D printer to follow, and then it just executes it. So it's kind of funny because as advanced as 3D printers look, they're actually pretty stupid, right? You can tell it to do like certain things and it'll just be like, okay, and then it'll try and do it and then it could break itself. So, obviously don't write your own G code unless you're kind of experienced with it. But, 3D printers will just kind of listen to the command and then try to do it. And it'll do it even if it crashes. So you need good splicing to kind of avoid those problems. Most of these slicers don't really have any issues, but, it's kind of interesting that this machine looks so cool and so advanced, but it's literally just a really long list of positional instructions, and it's just like, go here, like turn this motor, like push this amount of filament out in between like these 2 points, and then the printer's like, all right, I'll do it, and then it'll try to do it. So yeah. All right, so who needs more time to download this? It might take a little bit of time, but it shouldn't be too fast. Okay. Usually takes a bit to open this window. But yeah, we're using Prusa Slicer today. I guess a little bit of history for you. Prusa Slicer is based on another slicer that people don't really use as much anymore, but it was called Slick 3R. It's just slicer with 3 instead of E. So Prusa Slicer was kind of based off of Slick 3R's original code, and then they kind of did their own stuff. They made it a lot more advanced. But there's a lot of other slicers that build off of it as well. So Bamboo Studio, made by another company called Bamboo Labs, is also kind of based on the Slick 3R's code, but then they also took stuff from Prusa Slicer, and then they added their own stuff. And then Orca Slicer, the one kind of on the bottom, is kind of a mash of Prusa Slicer and Bamboo Studio. So a lot of these slicers are kind of based off each other, and they kind of bounce ideas off each other. Once a slicer gets a new feature added, the other slicers kind of get those features added within a couple weeks or a couple months. So slicing is all pretty similar. They're usually all pretty based on the same base code. And the nice thing is that they're all like free, except for Simplify 3D, but not a lot of people use that anymore. Yeah. Personally, my preference is Orca Slicer, but it's mostly because I'm printing with a Voron and I want more settings that I can be able to change. But Bamboo and Prusa Slicer is usually pretty good for almost all applications, unless you're doing something like really stupid like me and making really fast printers. But anyways, who needs more time with this? We good? Okay. So when you open it, you should be welcomed with this kind of wizard thing, and you just kind of want to run through it. It'll ask you to log in. If you want to make an account, you can. I'm not going to, just for the sake of time. It's not a big deal. It'll ask you what kind of printers you're interested in. So we're kind of interested in the FFF 3D printers. And you'll see in a bit, but each printer has their own profile, right? Each printer has like different size constraints, different speed constraints. There's a bunch of different parameters that, need to be tuned properly. The nice thing is when you buy most 3D printers today, they already have some default profiles that you can use. You don't need to build them yourself. So we're going to be using some Prusa profiles today. I'm just going to leave them all checked though, just so you can see there's a bunch of them out there. Oh, now it wants to download the profiles again. Great. Okay, so you can see here there's a bunch of images of different 3D printers here. Just for consistency's sake, we should all be picking the same one, because theoretically, if you pick the same one and you slice the same part in the exact same way, you should get the same output as I do. So please pick the same one that I'm picking, just so when I grade it, I'll know that if the time is off, then you did something wrong. So for this purpose, we're going to be using the Core 1L with the high flow 0.4 millimeter nozzle. So this one that I already checked here, I don't know if it's checked by default at this point, but you want to make sure you add that, right? Don't check any of these other boxes because these different profiles might have different speeds and stuff like that, and then you'll get different outputs. So for our sake, we're just picking this one. It's just the first one in the top left. So yeah. If you just keep on going next, you can add more stuff like the SLA printers that Prusa has, but I'm not really going to mess with this stuff. You can see here, if you have a printer from another manufacturer, they might upload their default profiles to Prusa and then they'll add them here. We're not adding any of these today, but you can see here, if you have, okay, don't click it. If you have another printer, you might be able to find it here, but I'm not going to add anything. So you can just press finish. Great. But then you should have some kind of area like this. Similar to Fusion, you have this nice build area. I did not want this. But you should be presented with this kind of workspace here. This is just kind of a virtual build plate. So, your 3D printer has some kind of platform that it builds off of, and it has, in the slicer, you have some kind of rendering. To navigate, just left clicking will help you spin around, and I believe right clicking is panning side to side. And then you can like zoom in and out and stuff like that too. So the controls are, I think, a little bit different to Fusion, but you can kind of get used to it. On the left side here, it allows you to change some parameters, not all of them. In this case, here you can pick your layer height. Here's your filament. Different materials have different melting points and stuff like that you need to account for. For this assignment, we just want to make sure it's generic PETG, because if you have a different material, it might give you a different output, right? If you don't have this, you can add or remove like filament profiles with this button, and then you should be able to find generic PETG. For the printer, you should only have one. I have two because I accidentally added another one. But again, we should be using the Core 1L with that high flow 0.4 millimeter nozzle. Underneath that, you can enable supports and adjust infill. But that's not all the settings, right? I was talking about perimeters and stuff too. If you go under the print settings tab up here, it gives you a little bit more control over the parameters that you can adjust, right? Under layers and perimeters, you can change how many there are. You can change, layer height here, top and bottom layers. The main thing you're going to be changing in this tab is perimeters, but all of this is available to you. For infill, you can change the density, but you can also change the pattern at which it does that. I'm going to leave it as grid. Again, if you change anything, it might add time and stuff like that, so you might not get a consistent result. So minimizing these changes, or just at least copying what I changed for this assignment, is what you should be doing. But these are all available to you. If you wanted more parameters, if you're getting a little bit more advanced, you can change the modes, and then it'll add like a crap ton more stuff that you can change. But we don't really need to for this assignment, so I'm just going to leave it nice and clean in this beginner mode here. To go back to kind of your build plate, there's this platter on the top left, and then you're kind of here again. Yeah, that's kind of basic navigation. Obviously, we don't have anything here, so we need to add some kind of model. So what we're going to do is we're going to add the 3D Benchy. So underneath that download link, there's another link that goes to printables. I kind of talked about online repositories last week. This is another one of them. I forget if I mentioned them or not. But this is printables is, a nice website to go to. People upload their stuff all the time. I upload stuff. And they're mostly free. So here you can download the 3D Benchy. Don't download these G-code files. You want to download the actual model in this case. In this case, it's an STL file. So you just download this. And then you can drag and drop, or you can, file, import, or Control I or Command I, whatever your heart desires. Okay. Yeah, once you insert your part, you can see it'll render that model on your build plate. And now you can make adjustments to the parameters depending on your 3D print and what you're going after. Does anyone need more time on this? I'm assuming it's pretty good. Okay, so everyone should have this now. You can see here on the bottom right, there's this Slice Now button. This will basically generate the tool path, right? I'm just going to hit it now just to kind of show you what it does. Obviously, we haven't applied the parameters that we are looking for, but this might give you kind of an idea of how the printer works. So it'll slice the model. Okay. So I'm going to switch back and forth between the editor view and like the slicer preview. This is currently the slicer preview, and this is what your model should look like when it comes off the build plate. You can see there's kind of this stair-stepping effect on this top surface, right? It's because it's a very shallow angle. If you look at the 3D model, it's nice and smooth, right? But because the 3D printer slices planarly, it'll kind of stair-step when it hits stuff like this. So it's technically like an approximation, but it's pretty close that it's usually pretty good for most applications. On the left, or on the right here, you can see kind of the slider, this vertical slider. to give you kind of a preview on how each layer builds on top of each other. You can see here, like, there's infill, right? It's hollow. The infill is 15%, so there's not much inside. You can see here that there's two lines, one orange and one yellow, for the two perimeters, right? So if we go look at here, there's two perimeters, right? So there's the orange outer, that yellow inner. And this can give you, a good idea of what's going on with your printer. So it'll start here. You can use this bottom slider to do the per layer preview. But you can see it'll just draw the 2D profile. It'll go up, in this case, 1.5 millimeters. And then it'll just keep on building it up and up until your part is finished. So looking here, we have some information about the part that we're slicing. It'll tell you how much it weighs, how much it costs, depending on, the material you're using, and how long it's going to take, right? In this case, we're going to be changing some of these parameters, and you're going to see that these values are going to fluctuate. So I'm going to go here. Okay, and I'm going to start applying these parameters. So some of these aren't parameters that you're typically going to be using, at least for this model, but I'm just asking you to use them just so you know how to select it. The main one I'm talking about is supports, because the 3D Benchy is kind of a torture test for 3D printers, and you're not supposed to use supports. But for this demonstration, I'm going to ask that you do use them just so you know how to use it in the future. But here, in our case, we want to apply, or we want this model to have 3 perimeters. We want to adjust the resolution, or the layer height, and the profile. We want 20% infill, and we want supports on. So you can see here under the print settings, like I said earlier, you can change the layer height. But for this machine, there's multiple profiles for each layer height. And that will affect how the printer performs. So there's the balance profile and the speed profile. For this assignment, you should be picking the speed profile. You can see every time I change a parameter, the slicer will kind of look strange, or at least the preview will. And it's because every time you make a change, the printer or the computer needs to recalculate the toolpath, right? Especially if you're adding perimeters or layers, your printer, or it needs to be recalculated before you can send it off. So I'm going to adjust the perimeters. I'm going to change the infill here. Again, I'm just changing the percentage. I'm not changing the pattern. And then I'm going to enable supports. So you can either do it here, auto-generated supports, or you can change it here. It should just be set to everywhere, in this case, just for consistency. So don't do build plate only, just do everywhere. But you can see now, this model looks see-through and stuff, and it's because the toolpath needs to be regenerated. So we have to slice it again. It'll do its thing, and then we'll have a different toolpath. Okay. So now things are looking a little bit different, right? And the main thing in here is all this green stuff. Those are the support materials that the slicer added for us. If we kind of go down here, you can see it looks a little bit different now, right? There's one orange line and then 2 yellow lines because we added another perimeter. You can see the infill density is a little bit higher. So that's kind of what we're going after here. So if you did everything right, your model should look like this. For the time, the normal mode should be about 1 hour and 16 minutes. I think if you're running a Mac, it has like 1 hour 15 minutes for some reason. So I guess it just rounds differently. But your time should be, you know, within 1 minute of what I see here. And if you didn't have it, or if this number is completely off, then you're likely missing some kind of parameter, or you may have changed something on accident. If you change like the infill and the perimeters before you mess with the layer height, in this case, you know, let's say I want to change to 0.2, it'll give you like this pop-up saying like, hey, you changed these things. Like, do you want me to transfer it over? You know, if you say no, obviously it's not going to do that, and you're going to have to reapply them. So if you did that, then that could be a reason. But yeah, that's kind of the basics of slicing for you. It's not super complicated, I hope. Yes? Any confusion here? No? Okay. Yeah, that's the basics of it. Obviously, you can go really deep into it, especially when you modify the printer profile. You know, a lot of the things I do in my free time is messing with the profile to see if I can make my printer faster. You know, maintaining or increasing speed while maintaining quality is a kind of a fun challenge, especially when you build your own 3D printer. So, you know, if anyone was interested in that, I can definitely talk about that stuff later. Because, yeah, I'm kind of in way too deep with this kind of stuff. I guess like a fun thing to look at here. Over here on the left, when you're in your slicer preview and you're kind of moving this slider here, this is exactly what the 3D printer is reading, right? And, you know, to us, it may just look like a bunch of jargon, but you can see, you know, there's a bunch of X, Y, and Z positions, along with E and like a bunch of other commands. But that's basically all the 3D printer needs to make a part. It's just a giant text file, and it just reads it line by line. And if you look, there's very, very small incremental changes, right? It's like 143.063, and then the next command is like 143.264, right? So these commands are very, very close together. Like these G-code files are typically like thousands or maybe even millions of lines long, and they're all just like movement commands or just like small macro commands. So if you are super nerdy like I am, you can kind of read these, which is kind of sad, but I guess I can read them now. Like G1 commands are typically movement commands. I believe G2 is like an arc command, so you could command the machine to move in a circle. But then there's a bunch of other commands that you typically see at the beginning that like tell the printer to heat itself up and stuff like that, or turn on fans, right? So if you ever, you know, go deep into modifying your printer, you're probably going to be reading G code or even making your own little macros to control the 3D printer. So it's kind of fun. But yeah, that's about it for this assignment. So if you did everything correctly, you know, hour 16 minutes, just make sure you screenshot this so I can see the time in the model. Hello. Yes. They turned out like pretty well. I'm pretty happy with them. Isn't it? I know. Yeah, you can take them both if you want.
Which ones?
All the skinny ones.
There's three.
Yeah, go for it.
Someone doing the mouse.
Yeah. But yeah, that's basically it for this assignment. You just have to screenshot it. That's about it. Any questions about slicing? No? Okay. All right, so now that you kind of know how to slice and you know the general parameters on how to do that, I'm going to talk a little bit about the limitations to 3D printing, right? We talked about supports a little bit, but there's a bunch of clever things that you can do to modify your design and make it easier to print or print better, right? And you're typically, designing these things around the limitations to your manufacturing process. So one of the big things that people talk about is overhangs. Basically, there's a point where you kind of do need supports when the overhang kind of goes beyond a certain angle. That kind of depends on your 3D printer, but the kind of rule of thumb that most people use is about 45 degrees. You can see here on the left, the overhang is not very aggressive, right? It's maybe like 5 or 10 degrees, and it's something that the printer can manage pretty well. I guess if you look at the slicer, all right, I'll modify this. Oh, I'm gonna turn this off. But basically, how the printer works, right? Because it's stacking the layers, you need to make sure the previous layer has something to build off of. And when you go at too extreme of an angle, it's going to make that a little bit harder for the 3D printer to reproduce your model. So one of the reasons why the Benchy is printed so often is because it has certain features that are difficult to reproduce. So one of those sections is kind of the overhang on the hull, right? This hull juts out at a pretty aggressive angle. So if we zoom in really, really closely, you can see the individual layers, right? Especially at the bottom where the overhang is kind of the steepest. You can see here, the first layer is here, but the next layer extends quite a bit farther beyond the first layer. And if we look at it from kind of the top perspective, you can see like the black area is the previous layer. When it prints these, you can see the orange perimeter extends almost entirely beyond this original perimeter. So there's not a lot to build off of. In this case, it's basically 0, right? And that's when you start to get some drooping, right? So there's nothing for this material to hang on to, right? There's like maybe a sliver right there. And that's just because the overhang angle is so high, right? So, typically you want to keep it within about 45 degrees. Lots of printers now have pretty good cooling, so the plastic will like harden, a lot quicker. So you can get, a higher angle here. Some people push that number to like 60 degrees as kind of like a more like aggressive maximum. But 45 degrees is typically the standard. It's also like pretty nice just when you're designing stuff because you can just apply a chamfer to something and the standard chamfer angle is 45 degrees. So you'll kind of see like if a 3D printed part was designed well, a lot of people will just put a bunch of chamfers everywhere. One thing to note is like chamfers versus fillets. So you know how to use both tools, right? And in the 3D model, like the fillet is rounded, but the chamfer is flat, right? Depending on which orientation your print is at, the fillet may be kind of a bad option, right? Because if you think about the circle, I guess it's good to see on the next slide. If you think about a circle, like this area here has a very high angle. So if you're printing something flat with kind of that fillet on the bottom, those first couple layers have a very steep overhang and then they're going to droop. But if you print with a chamfer on the bottom face instead, it'll be nice and easy. It's a nice 45-degree angle, and your print will come out a lot cleaner. So that's kind of overhangs for you. This is another example of overhangs. In this case, it's kind of the reverse, because for a lot of holes, the top part of the hole is an overhang, right? So you can see the top of this hole isn't very round. It's drooping a little bit. You can see that on the benchy as well, with like those little holes up here. You can see this blue line is the bridge, right? You can see as you making this feature, the overhang is getting steeper and steeper. There's not a lot of overlap here to the point where it just has to bridge across. And when that bridge happens, because again, molten plastic, it might droop a little bit if you don't have adequate cooling. So you might get holes that look like this when you're printing in like the vertical direction. Depending on what you're designing, that may not be ideal, right? Typically want round holes. But there's a couple workarounds, right? One of the things that I find myself doing a lot is doing this kind of teardrop shape instead of a normal hole. And that, you know, creates a 45-degree angle on the top of the hole instead of, you know, those overhangs, right? And although it's not exactly a hole, for most cases, that teardrop is, you know, adequate enough. Like it's going to retain, you know, your screw or whatever that you're using. And, you know, you don't need to drill out the hole or something to kind of remove that overhang. So adding that kind of profile can be kind of useful in some cases. You know, same thing goes for these arches. It's the same thing. It's just like half a circle, but you know, the top of that arch is an overhang. So like right here, you can see the slicer marks overhangs or bridges as blue. You can see there's a lot of blue here. So, you know, if you're optimizing this model and you wanted it to be easier to print, you could stop the arch short and make it go straight up and down. Obviously, you know, for aesthetics, in this case, you want it to be curved. But if you have the opportunity to limit or to eliminate the need for supports without impacting your design, you know, that's something you might want to consider. All right, so I was talking about bridging a little bit earlier. It's very similar to overhangs, but 3D printers are capable of producing short bridges. It's basically just having material span across two different points, right? These blue sections are bridges. The biggest bridge here on this model is right here at the window, right? And again, when you print the 3D benchy, you typically don't have supports, but you have this big span that doesn't have anything supporting it underneath. And 3D printers can reproduce this with, you know, a good tune and, you know, making sure that the bridge isn't too large. But you also don't want to make them too big, right? I specify, you know, like, you know, hey, don't use really long bridges because it'll droop. And then I had somebody submit me like a Golden Gate bridge, and it was basically all like bridging as a bridge too. So it was kind of funny to see that, but I prefer you don't do that, just because, you know, their model was, it was a nice model, right? They modeled it really well. It was very detailed, but when we printed it, it was like this big. All the features were super tiny, and when we gave it to them, it literally like broke in their hand, and it made me kind of sad. I think they were pretty sad too. So I don't want that for any of you. And one of those things, you know, please don't have excessive bridging if you can, you know, if you can design it out. Again, if the bridge is too far and it needs to be there, then you can add a support, or I guess I'll add the support when I slice your models. But if I see something that, you know, could have been prevented with, you know, different design choices, then, you know, that might be something I'll point out. But yeah, please don't do long bridges unless you really have to. Okay, so this is a little bit of a more like nitty-gritty kind of thing, and I think it kind of pertains more to people who use the 3D printer, but you can mitigate some of these issues in your design. um, you know, when you 3D print certain objects or just every object, right, you're heating up a material and then you're cooling it down. And when you heat cycle that material, it'll expand and contract. And depending on your model or the material, those like contractions can impact the physical model itself, right? Depending on the material, some materials are more prone to warping, but basically once they cool down, they're going to pull inwards and sometimes they'll curl on the ends. So you can see here, someone was printing this box here, and there was a fair amount of curling here on the ends. It's because, the material cooled down and it lifted it, and it, definitely not something what they were, or that they were intending for. So because of that, obviously this part isn't usable anymore, but there are a couple of things you could do to mitigate this. One is, have a well-tuned printer, right? But that's kind of on me because I'm printing your finals. But the other thing you can do is you can reduce the stress concentration areas. So like this box is very square and those corners are very sharp, and those sharp areas are where the stress is going to be highest. So to reduce that, you can add fillets. So again, depending on the orientation of the model, you might want to use a fillet or a chamfer, right? So on the bottom faces or vertical faces, you want to use chamfers, but on all these horizontal, like outer perimeters or edges here, you can use fillets, right? If you add a fillet, it'll kind of spread that stress out over a larger area. So, the forces won't be at super high at certain points, and it's less prone to kind of curling in this manner. Sometimes it's kind of difficult, especially when you have really, really long prints, right? The longer your print is, the more material is shrinking. So if you have a really long part, it's more prone to warping. So, most of your finals are usually not that large, but it's something to keep in mind. If you're printing stuff and everything keeps warping and you're like, why is that happening? It could be because your model is super long, your build plate isn't clean, stuff like that. Elephant's foot is kind of this interesting thing that happens when your printer kind of squishes the first couple layers. A lot of people, when they tune their printer, they usually have the first couple layers press into the build plate a little bit just so they get better adhesion, right? It's probably better that your part doesn't fall off while it's 3D printing. So a lot of people kind of squish the first couple layers. And when that happens, the printer doesn't always account for that extra squish. So the material that you're extruding kind of leaks out on the corners and the bottom kind of pushes out. So if you've ever seen an elephant's foot, the bottom kind of fans out, and that's kind of why they call it this. But you can see here, in this case, there's like this theoretical model, and they want this straight wall. But the first couple of layers are kind of squished out, right? And if you have like two parts that fit into each other, this can kind of prevent them from fitting into each other correctly. Again, part of it is on the person operating the machine. If I tune it well, then there shouldn't be excessive amounts of elephant's foot. But one of the ways you can kind of mitigate or eliminate this being an issue, even if it is a thing on your 3D printer, is again adding a chamfer, right? So if you add a chamfer on this bottom face, you kind of cut it here at that 45-degree angle, and then if there's any elephant's foot, it'll push outwards, but it still likely will be like beneath this, vertical face here, right? So if you add chamfers to the bottom face, you kind of eliminate the issues that come with elephant's foot. So that's something to keep in mind. I don't know if it was a good example. Okay, so this is a good example. So this person printed a phone stand. See, they have this bottom face here, and then the bottom edge is completely chamfered, like most of the way around. If you feel really closely, if you run your finger on the edge, you can feel like a tiny lip. And that's like just a very slight squish out from like the first couple layers. But this isn't really an issue. But that should really Yeah, I hope that makes sense. Uh, Basically, okay, the other thing is, like, the nice thing about 3D printing is that you can get really crazy geometries without adding cost, right? Because you're 3D printing it, you can make really weird shapes and it doesn't cost anything extra. When you're like manufacturing for like subtractive manufacturing, every feature you add costs money, right? But when you're 3D printing stuff, you can kind of go ham. So once I finish like the general geometry of my design, I'll just start throwing like fillets and chamfers everywhere to make the part look nicer. Um, and again, it's basically free. So if you can do it, it's something that you might as well do, unless you don't want to. But yeah, chamfers and fillets, they're pretty nice. In terms of tolerancing, 3D printers aren't the most precise machines. You can get them pretty dialed, but they're not perfect, right? Nothing's perfect. If your 3D printer's tolerances are kind of, or I would say like the worst tolerances people usually get is about like 0.2 to 0.4 millimeters. So I don't have my calipers with me, but it's a small amount. But if you need things to fit really well together, that is something to consider. I think my printer's pretty dialed in, so it's usually around like 0.1 millimeters. But when you want two things to fit together, you don't want the dimensions in the CAD to be completely exact, right? So the next slide I think is a good example. Someone made this Lego looking like model for their final one year, and they didn't add enough tolerance, right? And when I mean that is like one side should have been slightly smaller, or the other sides should have been slightly bigger. If you have zero tolerance, then when you go to put things together, it's not always going to fit, right? The prints aren't exactly the dimension that you set in the CAD, so you might want to undersize or oversize things a little bit. So for holes and stuff, like when I design things with like M3 hardware, which is kind of my preference, I use that a lot. I typically oversize a hole to maybe like 3.2 or 3.3 millimeters if I want the bolt to go through smoothly. And then, if I want to thread the screw into the model, I might set it as like 2.8, right? So there's a little bit of material that I can screw into, or I can oversize it a little bit so it slides through nicely. So when you're designing things that interface with other parts, which is pretty common, you want to make sure you add a little bit of tolerance to that. Yeah, that's basically it for today. There is a quiz, I forgot to mention, but there is a quiz for most of the stuff that I talked about today. But like, don't freak out because you have infinite attempts and stuff. So this quiz is mostly just kind of a little checklist for you to run through, for you to think about. So yeah, you're welcome to take the quiz now. That's basically your homework for this week. So pretty light, pretty quick today. Yeah, that's basically all I have. But yeah, so you're welcome to go. Next week, I will be bringing my 3D printer to class, and I'll be running a demo. So if you want to see a 3D printer running, next week is the week to come. I guess now is a good time to talk about the final. I did talk about it briefly at the beginning of class, but in terms of due dates, the final is going to be due 1 week from the last class. So, week 5 is next week. And then it'll be due at midnight the following Monday. I forget what date that is exactly. So it'll be due, yeah, the 27th at midnight. But yeah, when you once you finish your final, you will have the opportunity to have it 3D printed. Again, I passed around some finals from last class. So if you want your models printed, you can upload them to the Google form when it's posted next week. Basically, you just want to export it as an STL or a step file. There is a slight difference between the two. Personally, my preference is step files. I can kind of go into it a little bit. But basically, an STL file stands for like standard tessellation something. I forget what the L means. But basically, it converts your 3D model into a bunch of little triangles. And, you know, sometimes that's good if you don't want people modifying your design. But for the most part, it will kind of make your part a little bit worse, especially when you're printing at really large scales. Like when I was printing like a really, really large like cylinder, you could see the individual triangles on each of the faces around the circle, right? Because it's like an approximation instead of it being exact. So it'll have slight defects. So I personally prefer the step file over the STL file. I think it's becoming a little bit more common, but a lot of older files are STL only. But slicers can read both step and STL files. So if you want to give me a cleaner model, send me a step, because you know those will retain any curved geometry. All the faces are all intact instead of like it being an approximation. I'm getting your exact model. So yeah, please use steps. But if you want to use an STL, you can. So once you model your final, I'll probably talk about this next week as well, but you just go under like file export and then you save it as a step or a STL. So don't send me like the F3D file. I just want the step because that's what the slicer reads. So yeah. Are there any questions about the final? I usually get like a bunch of questions. I try to cover most of them before people ask though. Oh, size. Okay, in terms of size, I usually leave it up to your judgment just because, you know, the models that everyone sends to me are all very different shapes. And, you know, some things are really skinny and really tall, like the rocket ship that someone sent me, right? Or some things are really large and really flat, like someone sent me like a license plate, right? Like, so it's kind of hard for me to give you a hard number on how big your model should be. So I usually just say like, please be reasonable. My 3D printer can print things like 300 millimeters by 300 by 250 millimeters. But please don't send me something that big because, you know, that's a lot of time, a lot of filament, and, you know, there's a good amount of you and I want to make sure everyone gets their model. Typically, I just say like something around the size of your hand that you can kind of hold would be appropriate. But if, you know, your model is slightly bigger, and you like, it really has to be that way, that's fine too. If something is like specifically needs to be a certain dimension, like please tell me, because sometimes I'll scale the models a little bit, because sometimes people CAD things and I'll import it into the slicer and it's like shooting out of my screen, right? So I might modify them or like modify the size to like my discretion. But if you tell me, hey, like this thing needs to actually be this length, so don't scale it, just let me know. Like I think one year someone gave me like a toothbrush holder and I didn't know what it was and I scaled it down and their like toothbrush didn't fit, right? So like if it needs to be a certain size, just tell me. But if not, you know, I might scale it just as a disclaimer. Okay, I'll show you this. Is it save as? Or I think it's export. Yeah, okay. So if you send it to me later on, it's just file, export. You know, as type, I think you have to scroll down. As step. Do they not have STL anymore? Oh, they do. But yeah, you can just step here, and then you just hit export when you're finished. Um, but yeah, that's basically it. I guess the other thing I can do is find you a good example of some more examples of like overhangs and stuff like that. It's not here. Might need to find it. I don't know if I have it anymore. Oh, here it is. Okay. So this is definitely a very like elaborate part. But this was a single piece that I 3D printed for a class that I was taking here at Purdue. And you can see like certain design choices were made to make sure this thing was printable with limited or no supports. So you can see here, like all of these angles are below 45 degrees. You can see here, I have these jutting out at a 45-degree angle. So a lot of these things can be accounted for when 3D printing. Here, I made it go 45 and then I had a bridge. I could have gone straight up and across, but then going at this angle kind of reduces that bridge length. Another thing that's kind of cool is you can utilize bridging strategically by modeling things in a certain way. So on the bottom of this chassis here, we wanted bolts to go through from the bottom. But you know, in doing so, you create this overhang area that your printer can't reproduce. And one of the things, or how the slicer would work, is it prints the perimeters first, and then it prints the other stuff. So for a hole, it will print the inside of the circle, and then it'll fill in the stuff around it. But, you know, if you try to print something in the center here, it's going to print in midair, and it's just going to droop, right? And it's going to be super sad unless you have supports. So one of the things you can do is you can model things in certain ways to kind of manipulate the slicer. In this case, there's kind of a progressive stack of overhangs. So you can see here, there's this feature that goes across, and the printer will bridge straight over, right? So it can do a straight overhang or a straight bridge pretty easily. So you can stack them progressively. So I had it going this way, and then the next layer, it went this way, and then the last one is here. And then that kind of builds up like an area that it can print for it to print this circle right here. So that's kind of like a little trick that I kind of picked up along the way. You know, modeling a feature like this takes a little bit of extra time, but it also can save you time in the future, right? So let's say, for example, you know, I wanted to print 100 of these. By adding this feature, right, it eliminates the need for supports, so I don't need to spend like hours of my time just like fishing out supports from this tiny hole, right? And applying it to, you know, a bunch of holes on this can be a big time saver. So things like that, they're kind of interesting. There's definitely a lot of things that you just kind of pick up. Like in this case, like I didn't even have the teardrop here. I could have added it here, but I kind of forgot. So yeah. Yeah, that's kind of a little bit more information for you. Yeah. Any questions? I know this is all like very technical and nitty gritty, so if you don't like absorb all of it in one day, that's totally fine. But I just think it might be nice for you to think about these things, just so you can create, you know, better 3D printed models in the future. But yeah. Also, if you have questions about your individual finals, and you don't want to like ask through the Discord, you can just DM me and be like, "Hey, is this like too big or too small, or should I change this?" Like, I'm pretty open to stuff like that. People ask me if they should modify their design a lot, so please ask us. You know, you can ask me, you can ask them. We're here for you. So, yeah, just please don't send me like a Golden Gate Bridge again because I don't want that to break in your hand. Cool. Yeah, that's about it. I guess we're getting out about 30 minutes early today. So, you know, if you need to go eat, get on with your life, feel free to go for it. But yeah, I'll see you all next week with a 3D printer. So.